Hey everyone, it's Miss Bell here again from the Science Lab, and today I'm going to be talking about one of the 6 major simple machines. Now, this particular simple machine helps us do work in everyday life. You can see it all around us as long as you know what you're looking for, and depending on how it looks and how it's measured, it will help us use less force when pushing or pulling or doing work.
So the 6 major simple machines are the wedge, the wheel and axle, the pulley, the screw, the lever, and last but not least, the inclined plane. Looking at these 2 ramps, we are able to see that one inclined plane is longer than this one. So this one is shorter and this one is longer. And that really determines how much force or how little amount of force you're going to need to do work, to either push items up that slope or to pull items down a slope. If the length is shorter, you're going to have to work harder. If the length is longer, you're going to have to still do work but not use as much force. And that is all determined by either how high your ramp is from the ground, both of these are even right now, and also how long your inclined plane is, which determines the measurement of angle of your slope right here, where your inclined plane meets kind of at a point where the ground is. So your inclined plane might make a 60-degree angle against the ground, or I don't know, maybe your inclined plane might make a 30-degree angle against the ground. And it all would look different, you know, depending on how high or how low your inclined plane sits against the flat ground, and that's going to determine how hard you're going to have to work to get things up. Now imagine these are hills or a mountainside. Are you going to have an easier time walking up a steep slope like this? Think about it. Or are you going to have an easier time, like my friend Dwight right here, are you going to have an easier time walking up a slope like this that's not as angled and not as steep?
So for this certain activity, you're going to need a board for your inclined plane. And here I have already measured every 10 centimeters on that flat surface. I'm going to place it on an item, which is a tub right here, at a certain height. You can use a stack of books, or you can use anything that will keep the same height as you adjust your inclined plane length. I also have some rocks here behind my tub and at the end of my inclined plane, because I need to make sure that since I'm just working by myself, everything stays put. So the first measurement I want to start at is the 20 centimeters. So I'm going to line up my 20 centimeters with the edge of my tub. So the height goes up to 20 centimeters length of my inclined plane. So I'm going to just pretend that my slope is only this long. If you take a look right here, I have a string scale. This is a measuring tool that we use in the science lab to measure either mass in grams, that's what the G is for, or we measure newtons, which is how much force it takes to get an object from one place to a different place. So you're lifting straight up, or you're lifting and pulling against an inclined plane. I have my awesome dinosaur right here, and I'm going to place him on the hook. Now, I'm not pulling anything yet, so the amount of force is 0. It's at 0 newtons. But I'm going to hook my dinosaur onto my spring scale, and we're going to see movement. Ready? I'm going to let go. On 3, 2, 1. We are able to see it move straight down. And with this particular spring scale, I'm looking at the very bottom of that green disc, and it says or reads 0.8 newtons. That's how much force is needed to go from a flat surface like a table or my hand and pull straight up into the air. Now I want to see what my little container of markers does. Is it heavier than the dinosaur? Do I need more force? Does it have more mass? Who knows? You can only tell by using the spring scale. So I'm going to show you again. It's at 0 newtons, so no force is needed right now because nothing is hooked on to my hook. I'm going to hook it on, hook the container of markers onto my spring scale, and I'm going to let go. Here we go. 3, 2, 1. Whoa, big difference. So my dinosaur only went to about here-ish, and right now my markers went all the way down there, and that reads 2.7 newtons. So if I had my markers resting on a table or my hand like this, it's at 0 newtons. I'm going to need 2.7 newtons of force to pull these markers up. I'm going to need more force to pull up my markers than I would my dinosaur. So I'm going to take my dinosaur with my spring scale and place my dinosaur at the very bottom of my inclined plane. I'm going to pull my dinosaur up to the 20 centimeters, and I'm going to read on the spring scale how much force I need in newtons to pull my dinosaur from here to here. Then I'm going to readjust the length to 40 centimeters and do the exact same thing. Put my dinosaur here, hook it to my spring scale, and pull those two together to read how many newtons or how much force is needed to bring it up to this length of an inclined plane. I'm then going to adjust one more time to 60 centimeters. So it's a much longer slope, it's less steep, not as hard to get up or pull, and I'm going to read the measurements on my spring scale at this particular length, 60 centimeters.
we know that as the lengths of our inclined planes increases, so they get longer and longer and longer, the amount of force that you need to go up or down, or to move an object up or down that slope, actually starts to decrease. So the longer the length of your inclined plane, the easier it is to do that work. The shorter the amount of your inclined plane, the more force you're going to have to use, which makes the work harder. So they are all at the same height, but they're all at different lengths. So going up this ramp is going to be harder than going up this ramp, but the easier of the 3 ramps would be this one, because you have a longer length to stretch out that amount of force. So you can tell by looking at our filled-in chart that our dinosaur and our markers needed the most force to get them from one position to a different position when they were going straight up. So if I took our board, our inclined plane, and held it like this, when it comes in contact with the table right down here, that's a 90-degree angle right here at this corner. So our dinosaur and our markers were lifted up like this, and that is what needed the most force. But our inclined plane helped reduce the amount of force, even though force was still needed. It reduced the amount of force because it was helping us do the work from taking our dinosaur and our markers down here and bringing them up here. Now our 20 centimeter length of our slope, that out of the 3 inclined planes, that needed the most force to get from the bottom to the top. That pulled our spring scale the furthest. And then when we increased the length of our inclined plane, we needed even less force. But we saw when our length was at 60 centimeters, that is what needed the least amount of force out of all 4 of those choices. So we know the longer the length of our inclined plane, the less force we need.